Preparing for a PLC programmer interview. You've reached Candy Mentor, and this video is for you. We'll walk through 15 key questions you're likely to face. For each question, you'll see a sample answer, followed by the key points to cover. Subscribe, like, and share, and drop a topic request in the comments. Question 1. What is a PLC, and why is it used in industrial automation? A PLC is an industrial controller used to automate machines and processes. It reads inputs from sensors or switches, executes programmed logic, and drives outputs like motors, valves, alarms, or actuators. I use PLCs because they are rugged, reliable, and designed for real-time control in harsh environments. Compared with relay panels, PLCs are easier to modify, troubleshoot, document, and integrate with HMIs, drives, and SCADA systems. While answering, focus on PLC purpose, rugged industrial design, deterministic control, input-output handling, programmability, reliability, and how PLCs replace relay-based control while integrating with sensors, drives, HMIs, and plant systems. Question 2. Can you explain the PLC scan cycle? The PLC scan cycle is the repeating sequence the controller follows to run logic. First, it reads the physical inputs into memory, then executes the program using those input states, then updates the physical outputs. It also handles communications, diagnostics, and internal tasks. Scan time matters because logic does not execute continuously in the analog sense. It executes once per scan. That affects one-shots, timers, interlocks, and fast-changing signals. Make sure to cover input scan, program execution, output update, housekeeping or communications, scan time impact, and why understanding scan order matters for troubleshooting timing, latching, and sequencing issues. Question 3. How do you troubleshoot a PLC-controlled machine that suddenly stops running? I start with safety and make sure the equipment is in a safe state before touching anything. Then I check the HMI alarms, PLC status, safety circuit, e-stops, drives, and field power. Next, I go online with the PLC and trace the permissives or run conditions preventing operation. I compare expected inputs with actual input status, inspect wiring or sensors, and avoid forcing unless controlled and approved. After fixing it, I verify the root cause. In your answer, talk about a structured troubleshooting approach. Safety first, symptoms, alarms, input-output status, interlocks, power, network health, recent changes, forcing precautions, and root cause confirmation. Question 4. What is the difference between ladder logic, function block diagram, and structured text? Ladder logic is graphical and resembles relay circuits, so it is easy for electricians and maintenance teams to troubleshoot. Function block diagram is useful for process control, reusable function blocks, and signal flow, especially with analog or PID logic. Structured text is text-based and better for complex calculations, loops, arrays, and data handling. I usually follow the site standard, but I choose the language that makes the logic safest, clearest, and easiest to maintain. Be sure to mention where each language fits best: readability for maintenance teams, graphical versus textual logic, sequencing, math-heavy routines, reusable blocks, and why language choice depends on plant standards. Question 5. How would you program a motor start-stop circuit in ladder logic? For a basic motor circuit, I would use a normally open start input, a normally closed stop input, and a motor run output. The run output seals itself in through an auxiliary contact, or internal bit, after the start button is released. I would place overload, e-stop, guard, and drive-ready permissives in series, so any fault drops the output. Then I would test start, stop, fault reset, power loss, and restart behavior. While answering, focus on start and stop inputs, seal-in or latch logic, overload and safety permissives, output coil behavior, fail-safe design, and how you would test the sequence. Question 6. What are latches and unlatches, and when should you avoid using them? A latch sets a bit true and keeps it true until an unlatch resets it. It is useful for alarms, sequence steps, or events that must remain active after the triggering condition disappears. I avoid overusing latches because they can make logic harder to trace, especially after power cycles or abnormal stops. When I do use them, I make reset conditions explicit, document the intent, and ensure startup logic puts the machine in a safe state. Make sure to cover set reset behavior, retained states, power cycle implications, debugging difficulty, alternatives like seal-in logic or state machines, and the importance of clear reset conditions. Question 7. How do you handle analog input scaling in a PLC? Analog scaling converts the raw PLC input value into meaningful engineering units. For example, a 4 to 20 mA pressure transmitter might represent 0 to 100 psi. I map the raw count range to that engineering range, include low and high fault limits, and validate the signal against calibration data. I also consider filtering if the signal is noisy. The scaled value should be used consistently for HMI display, alarms, trends, and PID control. In your answer, talk about raw counts, engineering units, sensor range, 4 to 20 mA fault detection, filtering, calibration, resolution, and using scaled values consistently in alarms, displays, and control loops. Question 8. What is a PID loop, and how would you tune one? A PID loop controls a process variable, like temperature or pressure, to match a set point by adjusting an output such as a valve or drive speed. Proportional reacts to current error, integral removes sustained offset, and derivative anticipates rate of change. I tune carefully, usually starting conservative, observing response, and adjusting one parameter at a time. The goal is stable control with acceptable response time, minimal overshoot, and no hunting. Be sure to mention process variable, set point, control output, proportional, integral, derivative terms, tuning method, avoiding oscillation, loop response, and testing changes gradually under controlled conditions. Question 9. How do you design PLC logic for safe machine operation? Safe PLC logic starts with the risk assessment, not with code. Safety functions like e-stops, light curtains, and guard doors should use safety-rated hardware or a safety PLC where required. In standard logic, I build clear permissives, fault detection, controlled stops, and fail-safe outputs. I avoid automatic restart after safety trips unless the standard allows it. I also document reset behavior and test every safety-related scenario during commissioning. While answering, focus on risk reduction, safety-rated hardware, interlocks, permissives, fail-safe states, separation of standard and safety logic, diagnostics, reset behavior, and compliance with applicable standards. Question 10. What communication protocols have you used with PLCs, and how do you troubleshoot communication issues? I have worked with common PLC communication protocols such as Ethernet IP, Profinet, Modbus TCP, Modbus RTU, and Profibus. When troubleshooting, I check physical connections first: power, cable, link lights, termination, and shielding. Then I verify IP addresses, node addresses, device names, baud rates, and module status. I use PLC diagnostics, ping tests, vendor tools, and sometimes packet captures. Most issues come from addressing, configuration mismatch, damaged cables, or network changes. Make sure to cover common protocols such as Ethernet IP, Profinet, Modbus, Profibus, and serial links, plus addressing, device status, cabling, IP conflicts, diagnostics, and packet or module level checks. Question 11. How do you approach PLC commissioning on a new machine or process line? I commission in stages so problems are isolated early. First, I review drawings, network layouts, tag lists, and sequence documents. Then I perform I/O checkout with the field team to confirm every sensor and actuator matches the PLC address. After that, I test safety circuits, manual modes, interlocks, alarms, and automatic sequences without product, if possible. Finally, I run controlled production trials, tune settings, train operators, and document outstanding punch list items. In your answer, talk about staged commissioning, documentation review, I/O checkout, dry testing, safety validation, sequence testing, HMI verification, interlock testing, operator training, and controlled handover. Question 12. What is the role of an HMI in a PLC system, and what makes a good HMI screen? The HMI is the operator's window into the PLC-controlled process. It displays equipment status, alarms, trends, set points, and allows authorized commands like start, stop, reset, or mode changes. A good HMI is simple, consistent, and built around operator decisions. I avoid clutter, use colors meaningfully, show abnormal conditions clearly, and protect critical settings with security levels. The best screens help operators diagnose problems quickly, not just watch animation. Be sure to mention operator visibility, control commands, alarms, trends, set points, security levels, clear navigation, avoiding clutter, consistent colors, and designing for abnormal situations. Question 13. How would you structure a PLC program for a complex sequence? For a complex sequence, I prefer a state machine approach. Each step has a defined action, transition condition, timeout, and fault response. I separate automatic sequence logic from manual control, alarms, interlocks, and device-level routines. Good tag names and comments are essential because maintenance needs to understand where the sequence is waiting. This structure makes recovery easier after faults and avoids random bits controlling multiple parts of the process. While answering, focus on modular design, state machines, step numbers, clear transitions, permissives, fault handling, manual modes, reusable routines, naming conventions, and making the sequence easy to troubleshoot. Question 14. How do you manage PLC program changes in a live production environment? I treat live PLC changes as controlled engineering changes. Before editing, I back up the current program, review the requested change, assess risk, and communicate with operations. If online edits are required, I keep them small, testable, and easy to roll back. I avoid making changes during unstable production unless it is an emergency. After implementation, I verify the result, update comments or documentation, and save the new version with a clear change note. Make sure to cover change control, backups, risk assessment, online edit discipline, communication with operations, testing, rollback plans, version documentation, and avoiding changes during unstable production conditions. Question 15. Describe a difficult PLC fault you resolved and how you found the root cause. A good example is an intermittent conveyor stop that only happened during peak operation. The HMI showed a generic drive fault, but the drive history pointed to undervoltage. I checked the PLC logic, then trended drive status, motor current, and line voltage. The root cause was a loose terminal in the control cabinet, causing voltage dips under load. We repaired the connection, retested at full speed, and added a more specific alarm for faster diagnosis. In your answer, use a structured star-style story. Situation, symptoms, diagnostic steps, evidence, root cause, corrective action, validation, and what you changed to prevent recurrence. If you are still with us, congratulations, you are much ahead of the rest and serious about preparing for your interview. We hope we were able to add value to your preparation and create some helpful content. Do not forget to like and share this video. Your small act can do great things for us.